We have now come to a right understanding of the concept of chance experiments in the continuum in one and more dimensions. It is now time to test our grasp of the concepts and see if we can extend this to something which is more generic, more broadly applicable. So, to begin, I'm going to give you a sample function, p, in 2 dimensions, p of xy of the given form. Is it a density? Pause the lecture and have a go at it. Come back when you are ready. Sketching pictures gets more complex when the number of dimensions increases, but with 2 dimensions we can still make a good fist of it. If you have access to a good plotting routine or a symbolic manipulation program, you can plot what this function looks like, and if you do, this is what it looks like. It actually does look like a generic bell. Okay, and that reminds us, a faint atavistic tug to our memory, of the normal density, the bell curve. Maybe there is a connection, and indeed there is. Now, to verify the provenance of this function as a possible density, we have to check 2 things, positivity and normalization. Positivity is trite. Why? Because the exponential function is strictly positive everywhere, so it never becomes negative. And the question then becomes, is this thing properly normalized to unit area? Now, it's going to be clear that the integral converges. Why? Because the exponential function decays so absurdly fast. So the question now is, have I got the normalizing constants right? So, without further ado, let's set up a 2-dimensional integral of the given function. All right, we'll look at this and say, okay, in the usual course of things, when one is called upon to try to evaluate a 2-dimensional integral, we naturally try to do it iteratively. First one integral and then the other. George Polya would say, when you have 2 things to say first the first thing and then the second thing. Right? Naturally, we want to do things in an iterative fashion. Now, to do this, we want to take the function and try to split it up into the influence of x and the influence of y. And an examining of the particular form of the integrand tells us how we can go about doing this. There's a factor 2 pi in the denominator. We'll split it up into 2 terms, each square root of 2 pi. And then the exponential breaks up naturally into a product of exponentials. And now the integrand is a product of a function of x and a function of y. And these functions look strangely familiar. And indeed, of course, they are. Each of them is exactly the normal density, the bell curve, the function we called phi, following Gauss's notation. And so the first term in the integrand is just phi evaluated at x. The second term in the integrand is phi evaluated at y. And now we can simply separate the double integral into a product of 2 integrals. One involving the integral of phi of x, the other, for a different variable, the integral of phi of y. But remember, phi was a normal density. No further work is needed. We've already done the hard work. The normal density is a density in 1 dimension. And therefore it's positive, and critically, it integrates to unit. And therefore, each of these 2 integrals is identically 1. And therefore, we get 1 times 1, or 1, and this 2-dimensional function is positive and indeed properly normalized. And now we recognize its provenance. This is an example of a 2-dimensional normal density, a 2-dimensional bell curve. All right. A general verification will proceed along these lines, though of course the difficulty in verification will depend upon how complex the function is and how hard it is to do a particular integration. But the basic ideas are clear. Now, what made this particular construction work? Well, here is the key idea. The function I've given you decomposes into a product of 2 functions, each of which is a density. That immediately gives rise to an idea for a general construction in any number of dimensions. And so here, without further ado, is the assertion. Suppose I'm dealing with an n-dimensional sample space. And suppose that each of the trials is controlled by, determined by various density functions which don't have to be the same from trial to trial, right? You know, the discrete analog is of throwing dice where each die is differently weighted. In principle, one could imagine such an experiment. Suppose we have a sequence of one-dimensional densities. Let's call them P1 of the variable x1. P2 is another function possibly of a variable x2, and so on. Pn is a function of a variable, say, xn. Each of these is a one-dimensional density. In other words, each of these functions is positive and integrates to 1. The claim now is, if we simply multiply out these functions, well, naturally, we now get a function of n variables. Call it p. This function of n variables separates into a product of one-dimensional densities. The claim now is that if we do this for any choice of the constituent densities P1 through Pn, we will get a density in n dimensions. The verification now is completely trite. Right? Let's write it down. If you have densities in one dimension, if you multiply them, you're going to get a positive function in n dimensions. No problem there. The question is normalization, as always. What is the n-dimensional integral of this product? Well, we simply separate out the terms and multiply out one-dimensional integral at a time, n of them. Now, each of these one-dimensional integrals is the area under the curve of a one-dimensional density. By definition, each of those areas must be properly normalized to unit, and therefore each of the terms on the right must be exactly 1 without any further computation. And you get a product of 1s, and inevitably you get 1. So the product of n one-dimensional densities in fact gives you a density in n dimensions. We should conclude with a slogan. The product of densities is a density. Okay. At the heart of this construction is this key idea of multiplying densities. This is the fundamental key principle behind this concept of statistical independence. Independence is this cane, this thread, which runs right through this theory of chance. But I'm getting ahead of myself. We'll come back to this in a few lectures.